right. So Emma Luden is the founder of Space to Sparkle, an astrophysicist and space entrepreneur who is committed to helping ambitious humans find their place in space. As an astrophysics PhD student at Yale University, Emma studies the geometry of exoplanetary systems. Emma uses the kind of thinking spurred by this inquiry to help humanity develop a consciousness that puts the solar system in context. Earth's precarious position in the universe becomes clearer. She graduated magna cum laude with a BA in astrophysical sciences and minors in astrobiology and Latin American studies from Princeton University. Emma also is a space informatics analyst and Earth DNA ambassador. She is a co-founder of the Ask a Brookie mentorship program and the Princeton Undergraduate Women in Physics program. Emma is deeply committed to sharing her passion for astronomy to spark curiosity and excitement in future scientists, especially minorities in STEM. As a sought-after speaker, Emma travels around the world as a steward of the story of the next phase of space exploration and empowers the next generation of dreamers in STEM. You can connect with her via @exoplanet_Emma. And with that, thank you so much for being here. Take it away, Emma.
Awesome. Thank you so much for having me. I apologize for the technical delays at the beginning, and I am so excited to be here. Let's see, I'm going to share my screen, and please let me know if you can see it. Is it there?
We got it. Yeah, thank you.
Okay, perfect. And you can hear me now. That's all. Okay, awesome. So what I'm going to be talking about today, here, let me just get Zoom all organized. All right, awesome. So is Earth one of a kind? That is the question that underpins most of astrophysics. At the most fundamental level, astrophysics is humans looking up into space and asking, are we it? The evidence that we have to help answer this question is constantly changing as we learn more about our universe. And we know a lot more today than we did even 5 years ago or a couple months ago, to be honest. The goal of this talk is to put the Earth in context by exploring how, why, and where planets form. So a little more context on who I am. Emma, I go by Exoplanet Emma if you find me on social media. I'm a PhD candidate in astrophysics at Yale. I serve as on the National Committee for the American Astronomical Society to look at public policy, and I'm very committed to how science relates to the world. I have done other work with mentorship. I'm really committed to working with women in STEM in particular. And as mentioned, I'm very excited to start launching a program called Space to Sparkle this fall, which is going to be designed to empower ambitious undergraduate girls into careers in the space industry from astrophysics and physics. So with that, I'm going to talk a little bit today about something that relates to my research and how we can learn about putting the Earth in context in the universe. So this is what is known as the pale blue dot photo. It's one of my absolute favorite photos in the world. What we see in the front, in the foreground, is Saturn's rings, which are those yellow lines. And then we see Saturn, kind of the light of it is blocked out in that upper left-hand corner. And then down where that arrow is one tiny little dot that's like about the size of a couple pixels on your computer screen. And that is Earth. On that is our entire society. All of our history, everything that has ever been is right there in that like little speck of light. So this photo was originally taken from a little bit of a different perspective in the 1970s when Carl Sagan convinced NASA to turn the Voyager space probe around and take a picture of Earth. And I've always found this photo to be inspiring for my career and for what I love to do, because it really helps to show that our Earth is just like this tiny speck of dust. And to me, that puts a lot of what happens on our planet in context. And that's why I love to study astrophysics, because it puts all of our world in context. And while that's our tiny speck is one planet, Earth is actually one of many planets. Earth is one of over 5,000 planets that have all been discovered except for our own solar system in the past 30 years. Right before 1992, we thought that there were only our 8 planets in the solar system. Now we know that there are over 5,000, and that 5,000 is just the ones that we found. It's suspected that there is at least one planet around every star in every galaxy. And when there are 100 billion stars in every galaxy and 100 billion galaxies, that means you're talking about more planets than there are stars in the universe. So that begs the question then, what are these planets like? What are they made of? What are their structures? How are they in relation to each other around other stars? Are they like the Earth? Are they not? And to me, those questions are really fascinating because not only are they interesting from a scientific perspective, but they also tell us about our own Earth and give us context for life on our planet. So if we start with the 8 planets in our own solar system, we have these gorgeous photos of them. So these are real pictures of what those planets look like. They are these gorgeous, beautiful, high quality images because we can send missions to all of these planets and get pictures. The most recent addition to this is Pluto. The Pluto New Horizons mission was able to take the photos of it, or well, it'll be up there soon. Pluto's not a planet, but we still have a picture of it. And we can do that because we have the missions that can go to these planets. But exoplanets, the nearest one is 4 light years away, which means that there's just no hope of getting to it in our lifetime with the technology that we have right now. So we have to find other ways to study these planets. And to do that, we look at different parts of a planetary system. For our own solar system, we have 2 different kinds of planets. We have our rocky interior planets like Mercury, Venus, Earth, and Mars, and then we have gaseous outer planets, Jupiter, Saturn, Uranus, and Neptune. These photos are not to scale. The gas giants are much, much, much bigger than the rocky planets. And the rocky planets are all on the interior of the solar system, and the gaseous planets are all on the outside of the solar system. So if we put our solar system in full, again, huge caveat here, this is not to scale. We have our inner terrestrial planets that are the 4 most inner ones, and then our outer 4 planets, and they all orbit around our sun. This is one part of a planetary system. Sorry, I need to move this video a little bit. Okay, cool. So here we see our whole solar system in full. And we can kind of think about, as we extend our discovery or our knowledge of exoplanets, what are the parts of a planetary system? Well, the first part of a planetary system is a star. In our own solar system, that star is the sun. The next part are super Earths. I'm sorry, I'm seeing the text didn't show up properly, but that says super Earths. So instead of naming every single planet, imagine we were to just categorize the planets in our solar system into 2 categories. Kind of like how in grocery stores, you can have like an aisle of vegetables and an aisle of breads. And you can go in and you can name every vegetable and you can name every bread, but when you're delineating different parts of the grocery store, like you're delineating different parts of the planetary system, we can just go with broad categories. So our first broad category are super Earths. Super Earths are terrestrial planets. They don't have gaseous outer atmospheres, and they're generally smaller. We can also have gas giants like the Jupiter and Saturn, which are really, really big, super low density, and are typically found outside on the outer edges of a solar system. And then we also have the sub-Neptunes, which are gaseous, bigger than super Earths, but a little bit smaller than the gas giants. And altogether, those 3 different kinds of planets make up, or 3 different types make up the planets that we would see in a planetary system. So the way that we're looking at the solar system right now is from a top-down view. So we're seeing the plane that the planets orbit in, and they would all go around kind of like hands on a clock would go around. But we can also imagine tilting our view so that we're looking at it from a 90 degrees different. So we're looking at it from the side. So if we imagine looking at it from the side, we can picture all the planets orbiting in that plane around the sun. So it's like if you spin a top, you can look at the top from above, but you can also look at the top from the side. And from above, you could maybe see lines that are drawn on the side, on the like circular part of the top. From the side, you would just see a ring. So that's the ring that we're seeing here. And what's interesting is that in our solar system, we can also look at the angle between the plane where the planets are orbiting, that white line, and the axis the sun is spinning around. And that tells us a lot of information about the planetary system, and it is one of our components of a planetary system. So in this case, we're going to call that the tilt of a star. And the tilt of a star is this angle between the white plane that the planets orbit in and the line that's perpendicular to the spin axis of a star. So if I was spinning around with my arms out, it would be the angle between the plane where the planets would be and the plane that my arms are in. So our sun is tilted about 2.7 degrees relative to the plane where the planets orbit. For another example for how to visualize that, you can think of a system that's well aligned as when you stick a toothpick into a top of a pile of pancakes. In that case, we would call the system well aligned because the planets would orbit on the plane where the top of the pancakes are, and the star would spin around the toothpick. But you could also have a star that's spinning around a toothpick, but the toothpick is stuck in at an angle, and that would be what we would call misaligned. And that is all part of the component of the planetary system called the tilt of the star. The fourth component is called the tilt of the planets. So our own Earth has a tilt of about 23.7 degrees. Our North Pole, instead of facing straight up, it actually is tilted to the side. And that angle is why we have seasons. Because the amount of flux density from the sun that hits the Earth, basically just the angle that it hits us at as we go around the sun, is what causes our summer, winter, spring, and fall. So these tilts of the planets are really important for how life can form and what can be on different planets and what can be where on different planets. And Earth's not the only planet that's tilted. In fact, all of the planets have some kind of tilt to them. Mercury is only off by about 1 degree. Venus is like flipped upside down. Mars is tilted about the same amount as Earth, so it has seasons pretty similar to Earth. Jupiter is similarly off by only a little bit. Saturn is tilted a fair amount. Uranus is like on its side, so it rolls around. And then Neptune is tilted only a little bit. So we can put all of these together into what I call, let's make your own planetary system. So in this case, we're going to say our 4 components of a planetary system. So if you were making a planetary system, you would have to choose a star, and it could be a sun-like star, it could be a supergiant star, it could be a brown dwarf, it could be a pulsar. There are other kinds of stars, but the point is that it doesn't have to be a sun-like star. It can be other kinds too. You can choose planets, as many as you wish. You can have hot Jupiters, which are Jupiter-sized planets that are super, super, super close to the star. You could have sub-Neptunes, which is like our Neptune and Uranus. You could have super Earths, which are like the terrestrial planets. And you could have gas giants, which are like our Saturn and Jupiter that are farther out in the system. You would, for your third step, choose a tilt for a star, and then choose tilts for your planets. If we were to go through this exercise for the solar system, if we choose a star, we're going to first have the sun-like star, because our star is the sun. So we name things that look like the sun, sun-like star. We would choose to have 2 sub-Neptunes, 4 super Earths, and 2 gas giants, because that maps on the 8 planets that we have in our own solar system. And we would be able to pick our 2.7 degrees for the star, and then go through and pick our orientations for all the different planets, like we saw on the previous slide with all the planet different tilts. But our own solar system and our 8 planets are not the only ones. What we're going to see here is an illustration of some of the systems that were found as of, it'll walk through time, some of the other exoplanetary systems. So every dot on this slide is an exoplanet, and an exoplanet is a planet outside of our solar system. So all of these planets are ones that we'll never be able to get to. We'll never be able to get pretty pictures of, at least in the next 20, 30 years. And they're all different sizes, they're all different temperatures, and they're all strikingly different. If we look at our own solar system here in the middle, it looks very different than, say, this system over here that has one super small inner one and one outer one, or these ones that have a super, super big planet. So what this shows us is how different other systems are from our own solar system. And to me, that just begs the question of what makes the most common kind of planet? What is the most common type of configuration? What's the most common tilt for a star? What's the most common tilt for a planet? And what does that tell us about the universe? So exoplanets are a relatively new field. They were first found in the 1990s, and then the very first one was found in the 1990s. So it's been the past 30 years. And the big boom in discovery happened because of this telescope, which is called Kepler. Kepler was launched in 2008 and really revolutionized our understanding of exoplanets because it was able to find many of them, which has really opened our eyes to the diversity of planetary systems that are out there. So On this plot, I'm showing the cumulative number of detections. So however, how many exoplanets were found in total by the end of every year, and then discovery year on the x-axis. So as you can see, 1992, you can't even barely see, there was one planet found. And then it slowly built. By 2005, you maybe have like 10, 20 planets. And then Kepler launches, and all of a sudden you get this growth. And then a second telescope called TESS launched in 2018, and TESS is continuing to increase the number of planets that we know about and help us learn more about our place in the universe. So the planets that were found by Kepler are oh so creatively named, Kepler and then a number. In one case, a particularly interesting system is called Kepler 63. So we're going to go through our Make a Planetary System framework for Kepler 63. Kepler 63 orbits around a sun-like star, which is the most common type of star in the universe. So turns out that what we orbit around is actually pretty common to be orbiting around as a planet. This system only has one planet, and it has a planet that's called a hot Jupiter. And like I said, hot Jupiters are these weird planets that orbit super, super close to their host stars. So our innermost planet orbits it takes about 70 days for it to go around the sun. But these hot Jupiters go around every 2 or 3 days. So they're really, really close to their stars, and therefore they're really, really hot. They're about the size of Jupiters, and hence they're named hot Jupiters, because astronomers are super creative at naming things. This particular planet has an interesting orientation because it's tilted fully on its side. So if we look at our star in this top, it's like a toothpick stuck straight into a stack of pancakes. Whereas for Kepler 63, it will be like sticking the toothpick into the side of the stack of pancakes. So your star is going around like this, and then your planets are orbiting in the plane around it, but it's like rotating like this instead of like this. And to me, that's really interesting because from what we know about planetary formation, there's nothing that says that that should happen. And in fact, that shouldn't really happen all that much. We can also ask, what is the orientation for our planet? What's the orientation for the one hot Jupiter that orbits around the star? And that's a question that we don't have the answer to, because determining that tilt is really, really, really hard. You have to know the tilt of the star. You have to know a couple other different angles that we don't have the ability to measure right now. So there's really groundbreaking work happening in terms of figuring out what are the orientations of planets. But for the most part, that's an unknown part of these systems, which is interesting when you think about how we know, like the first part of this, we know what star planets are around. We can find most planets, although we have not found a lot of planets. And we can generally figure out at least a component of the orientation of the star, but we don't know the orientation of these planets. And that's a fourth part of the fundamental descriptors of a planetary system. So there's a lot that we still don't know in spite of the wealth of information that we've gathered in the past 30 years. So this system, if we have an artist representation of it, it would look something like this. I keep in mind, this is an artist representation. It's not a system or not a real picture of it because we can't get those. But what this is showing is that it would likely be an extremely hot planet. It would likely emit heavily in the infrared, and it would orbit super close to the star. So this is, if you were to scale, compare our Mercury and Venus around the sun to where Kepler 63 orbits around its own star. So as you can see, it is much closer in than even our closest planet. And it turns out there's a lot of hot Jupiters in the exoplanets, which is also something that's unpredicted because we don't fully understand how those kind of gaseous planets could form so close to a star. So that was one system. But as we saw, there are a lot of systems on that plot. The one that looks kind of like atoms. So I'm going to show you here a plot of all the exoplanets that we know of so far. And what we're going to do is look at it on the x-axis. There is their period. Their period is what we would call a day or their year. So for the Earth, it would be at about 365 days. So these are in scientific notation. So 10 to the 0, 10 to the 1 is 10. That's 100 days, 1,000 days. So Earth is about right here, about 365 days. And then our scale on the y-axis is in Jupiter masses. So 1 Jupiter mass is here, 10 Jupiter masses is here, And Earth is right down here at like negative 2.5 Jupiter masses. 10 to the negative 2.5 Jupiter masses. So Earth is a lot smaller than Jupiter, and it orbits at about 365 days. But those are all the exoplanets that we know of right now. And as you can see, they're very different in their different characteristics. A good part of my job is being able to look at a plot like this and pull out interesting information. Like, what can we visually see in it? So one of the things that I immediately notice in a plot like this is that there are three kind of distinct populations. There's this population up here where it's super densely packed that are orbiting at about 1,000-day orbits, or a couple hundred to 1,000-day orbits. And they're about 10 Jupiter masses, maybe a Jupiter mass. And then over here, you have these planets that are orbiting pretty short periods, less than 10 days, and they're also about Jupiter mass. And then you have another cluster down here that are orbiting, again, on pretty short periods, up to about 100 days, and they're much smaller. They're not quite Earth size, but close. And then there's this kind of line on the map, or on the plot, where there's nothing to the right of it. And that begs the question of, well, why do we not see the planets there? Like, that's where Earth is. Like, that should be the most interesting area to find about. And that's that line is induced by our observational limitations. Our telescopes can't see things that orbit at really distant periods or that are really small. It's pretty easy to find something that's super big and orbits super close in, or even something that's pretty big and orbits far out. And if it orbits close in and is small, then we can still find it. But something that's small and orbits pretty far away is pretty hard to find. So that finding an Earth-like planet is still the holy grail of exoplanet science, and something that hopefully will happen in the next 10 years, but we really don't know because it's all instrumentation dependent. We can also put on here which stars we know the tilt of. The tilt of a star in exoplanets is called the projected obliquity. So every star that's colored here is one that we know the tilt of the star for. So as you can see, there are a lot of planets that we don't even know the tilt of the star for. So there's a lot to learn still about all these exoplanets. And to me, that's why it's such an interesting field. We have our own Earth that is so different from what we know about other planets, and there's still so much to be learned about every one of these systems. We have different names for these different clumps of systems. The upper right quadrant is called the cold Jupiters because they're Jupiter mass and they orbit pretty far out from their stars. So as astronomers, like I said, are pretty creative with naming, it's called a cold Jupiter. For the planets that are closer into the system, or closer into the sun, and then our Jupiter mass, they're hot Jupiters, like Kepler 63, like we talked about earlier. And then there are these short period planets, which are they have shorter periods, hence they're called short period planets. Again, astronomers are creative at naming things. But like I said, what's interesting is that we don't know much about the other planets that would be around where the Earth is. So at minimum, what we can do then is we can probe short period planets and try and learn about them, because to me, they're the most interesting population because they're most similar to our own Earth. And if we want to understand our Earth and understand our own solar system, then studying these short period planets is a good way to start. I study these planets by using telescopes on the observatories in Hawaii on Mauna Kea. This is one of my favorite photos of the Milky Way above the telescopes. The telescopes are these white blobs down in the corner. And I, because of technology, I'm able to sit in my bed in New Haven in my pajamas in the early morning and control the telescopes from across the globe and collect data about these short period planets. From a practical perspective, this means looking at about 500 stars for the project that I'm working on and getting observations of it. Astronomers measure the location of things in the sky using parameters called right ascension and declination. And you can think of it kind of like latitude and longitude. Your right ascension is like your longitude and your declination is like your latitude. So when you look up at the sky, everything has a right ascension and a declination. And every single one of these dots on here represents stars that are being observed on the sky for my research. What I do is I look at the projected obliquity, the tilt of the stars, to figure out what that can tell us about the exoplanetary systems and how we can learn about them to put our own Earth in context and figure out, like, our own solar system was aligned, but why are most systems not aligned? And that's the question I'm trying to answer by looking at these 500 stars. So all the ones that have the light blue are stars that we know have planets around them. All the stars that are the dark navy, or all the dots that are the dark navy, are stars that are part of a control sample that we compare against. Because like any good scientific experiment, you have to have a control sample you can compare against. The green circles around the dots are ones that we have already observed. The ones with the pink X's over them are ones that are going to be observed tonight, actually. And at the end of this, we'll have a sample of 500 stars, and we'll know the trends in the tilt of these stars. And that can tell us about how these systems form. What is the most common type of formation? Do they form the same way that we think the solar system formed, or are we totally wrong about that? And could there be some other way that these systems are being created? So I've thrown a lot at you in the last 20 minutes, 25 minutes. So I want to bring us back to our question. Is the Earth unique in the universe? We don't know. There's still so much to be learned, so many planets to be discovered. What we do know is the idea that we have some privileged position in the universe is really challenged by the discoveries of other planetary systems that look nothing like ours. This dot, this pale blue dot, as Carl Sagan called it, of our home, is a reminder that our home, is one of many planets in the universe. And to me, that helps put our solar system in context, and our Earth's precarious position in the universe becomes clear. So I study astrophysics because I love learning about how to put our planet in context. Because to me, that puts issues like climate change in context. It puts issues like inequality on our own planet in context, and helps us to understand that at the end of the day, all of that strife, all of our challenges, all of it's happening on that little bit of dust and that little speck of light. And I hope that through learning about these exoplanets, you can walk away today with a little bit of a widened understanding of where our own solar system sits in the universe, where our own planet sits in the universe, and with a broader understanding of what kind of discoveries are out there and why those abstract and seemingly superfluous discoveries really matter here at home, why it's important to know how we fit into the universe, and how that can both help from a technology perspective, but also just from a philosophical perspective. So I would invite you to, if you're interested in connecting with me, I always am interested in talking about this. I share about it on social media, so please feel free to contact me that way, reach out. I am so excited to have gotten to share this with you today. I think that finding our place in space is one of the most powerful things that we can do. And I'm really grateful to you for joining me on this presentation today. So thank you.
Thank you so much. That was wonderful. I would like to invite anybody who has any questions to either put something in the chat. I think we probably, if you even wanted to unmute yourself, if you felt like turning your camera on, we could have a little conversation.
Yeah.
Are there any questions from the audience?
I have a question.
Yeah, go ahead.
So the map of the planet that was tilted, and then you showed like Mercury and Venus and how that orbit was wicked close to the sun on one side and farther away. So what does that tell you, like season wise? Is it like uninhabitable basically, because on one side it'd be like lava, on the other side it'd be freezing?
Yes, so that's exactly right, actually. So for hot Jupiter, so just to make sure you're asking about like the hot Jupiter, the Kepler system, is that correct?
Yes, is that what? Yes.
Okay, so yeah, so hot Jupiters undergo this really interesting thing where, because they're within like a 2 to 3 day orbit around their star, so their year is 2 or 3 of our days. There's this phenomenon called tidal locking, where they sync up so that the same side of the planet is facing the sun as like all the time. Kind of like our moon is exactly the same way. It's tidally locked to the Earth, so we see the same side of the moon all the time. Mm-hmm. And because of that, you have one side of the planet that is super, super, super hot and one side that's super, super, super cold. So there's some research about the atmospheres of those planets that suggests that they have really interesting weather, because you end up with this side that gets super heated and then it goes to the other side of the planet where it's super cold and you get like cloud movement basically around, that we haven't been able to observe in practice, but it's shown up in simulations. So it's something that's a super interesting topic for study that would produce very different weather, as we would call it, or climate even, on these hot Jupiters, and they would certainly be uninhabitable to life as we know it.
Wow, thank you.
Yeah.
Great. Thank you. In the chat, Ellen asked, how close are we to finding other planets with the same variables as our Earth?
That is a great question. Those are the holy grail of exoplanets. If I was ballparking, would say 10 to 15 years. Right now, the difference is that we just don't have the instruments that are capable of separating out the signal of a Earth to or Earth-sized planet. One of the ways that we can measure where planets are, or that they're even there, is through a method called radial velocity. And what that does is it measures the tug of a planet on a star. And that tug we can actually measure through looking at the light from the stars, basically. And the size of the signal that we would need is 10 centimeters per second. It's a velocity of 10 centimeters per second to be able to spot an Earth-like planet around a sun-like star. And right now, the precision of the instruments that we have is closer to 50, 60, 70 centimeters per second. So we have to drop a fair amount in our ability, in our error, the size of our error bars, to be able to find those kinds of planets. So, and the other thing that happens is that it's really hard to discern whether you're seeing signal from an Earth-sized planet or whether you're seeing activity on the surface of a star, because that can masquerade as a planetary signal as well. And we don't know how to distinguish that yet. We don't know how to separate it in our pipelines. And the other methods of planet detection don't really come close to finding Earth-sized planets. So it'll be a little while still. But you will hear all about it whenever it happens, because it is going to be like one of the biggest discoveries of the century if it happens this century.
Yeah, even 10 to 15 years, that would be mind-blowing.
Yeah.
Thank you.
Yeah, of course.
And Carrie asks, do we expect planetary tilting to change?
Yeah, so that's a great question. So our own planet, like I showed, it has the tilt of about 22 degrees. That's how we get our seasons. That tilt changes on a scale of about 25,000 years because of the way that we're locked in with the moon. And just like we suspect that every star has a planet, it's suspected that most systems probably also have exomoons. So while we can discover exoplanets, another interesting discovery would be the first exomoons, which have claimed to have been found, but that's a little iffy right now. But there are systems that totally could have moons that would lock them in such a way tidally that they could also have changes in their tilt. There's also, another thing that I study is how planets can get super tilted. Like, what is the process that takes them from like a straight up to like Uranus rolling around on its side? And that's not entirely understood. It's mostly to do with tides. But you can get these systems where the planet will like be like this, and then it'll be like this, and it'll just like go back and forth. So you can imagine the kind of havoc that would wreak on the climate of a planet. And so we're pretty lucky that our own Earth doesn't do that, and that the 23,000 year cycle that we undergo doesn't particularly affect our weather, because otherwise that could have really bad impacts for life on the planet.
All right. There's a comment from Gabriella that says, read National Geographic, Earth core, both solid and liquid, plus picking up strange vibrations that they're trying to decipher. Gabriella, I don't know if you have any specific question on that, or just wondered if Emma had a comment. Are there strange vibrations?
Yes, I read that both different articles in National Geographic, and I would just like her to expand on that.
Yeah, so the Earth has two different, it has a couple different layers to it. And so we know about the layers of the Earth pretty precisely because we can measure the waves that come from earthquakes, and we also have models that we can test for how the Earth's core is. So we know that there's a solid iron core, there's a liquid iron core, and then there's a couple other layers until you get to the outer crust. I don't know, I'm not familiar with the strange vibrations in the National Geographic article, but there's still a lot that we don't know about our own planet. So my guess is that it has to do with that, because like there are parts of the ocean that we haven't explored. There's parts we really can't dig that far into our own planet. So while we have these models that can pretty well explain what's going on, there's still so much unknown about even our own planet that it kind of blows my mind that we are studying these other 5,000 planets, and that there's just so much to discover.
Thank you. If I could ask a personal question about reading. I love a lot of science fiction works. I was just curious if you and astrophysicist friends do you get a kick out of reading these kind of planetary space opera type books, or is it kind of like, that's not even real?
So I, first of all, love libraries. I grew up just living in the library, local library during the summertime. And so I love to read. I love to read anything. I've gotten more particular about the science fiction I read. I think that's more of a personal preference though, because I find that I get more attached to characters than to civilizations, and the trend in sci-fi to follow a civilization for thousands of years doesn't appeal to me quite as much as following a character through a lifetime or through an event. Obviously it's a generalization, not all science fiction books do that, but I like ones like The Martian that are so thoroughly researched. That to me is really fun to read, because it just, you read it and you're just like, wow, that's right. And then at the other end of the spectrum, things that are just so different from our own understanding that it makes you question, what could other life be like? What could other civilizations be like? I love reading those too.
Good, great, me too.
So,
Thank you.
Which is your favorite Star Trek then?
Oh, that's quite a question. I love the new one, the Star Trek Discovery. I really enjoyed watching that. I love a badass female protagonist. So I can't at all complain about that. I mean, the original ones are also fun too. I'll never love an episode more than The Trouble with Tribbles. So
it's a good one. Oh, wonderful. Any other questions in chat, in person? All right. Well, Emma, thank you so much for being here. Space is fascinating, and this was a wonderful, very informative presentation, and we so appreciate you being here. And thank you to everyone for taking the time out of the day to attend this program.
Yeah, thank you all so much for attending, and it's been so great to interact with you even virtually, and I'm so happy to get to share this kind of perspective in any kind of format. So thank you so much.
Great. Keep up the good work.
Thank you.
Bye, everybody.